All right, the next talk will be given by Matt Yankowitz from UW.
All right. Thanks, Yanglong, for all the organizers for the invitation to be here at this very, very nice workshop. So I'm going to tell you some of the work that my group has been doing recently, investigating twisted bilayer graphene near the magic angle under continuous uniaxial strain. Since there's many people here who are not from the 2D materials community, I just want to give kind of a broad overview of the progression of this field over the years and computer is frozen. Good. The progression of the field over the years and how it's led to the types of experiments that we're doing today. So by now we've had 20 years of 2D materials that we can isolate with Scotch tape mechanical exfoliation from bulk crystals down to the atomically thin limit. And people have studied dozens and dozens of these materials, and we can basically classify most of the known phases from bulk crystals as analogs in two-dimensional materials. But the real power of this field is not just your ability to isolate individual materials and study them one by one, but to take these materials and to combine them into designer heterostructures through relatively simple procedures of basically just stacking them on top of each other. And the benefit of doing this is that you get emergent properties often in these composite heterostructures because the electrons in 2D materials live entirely on surfaces and therefore hybridize very strongly with neighboring layered crystals. So you can basically engineer new properties into materials by cleverly stacking and twisting the layers on top of each other. This is what an actual device looks like for transport measurements. So what you're seeing in the colors are many different flakes of graphite, graphene, boron nitride carefully stacked on top of each other and then patterned into a Hallberg geometry. And from a side view in a kind of cartoon schematic, the basic idea is that we're building a dual-gated field effect transistor. So we have our physics layer, and in this case, I'll mainly talk about twisted bilayer graphene that's enclad between two thin flakes of boron nitride dielectrics with graphite flakes on the top and bottom. So we can separately control the carrier density and a perpendicular electric displacement field by either the combination or the difference of the gate voltages. And what I'll show you is basically, as this field has evolved in kind of a seminal discovery from Pablo Herrera's group about 7 years ago, that if you stack and twist the right materials or you arrange layers correctly, you can in fact make a single material that you can tune between all of these different phases of matter just by changing the gate voltage that you're applying in the FET geometry. So taking a more modern view of this field, there's now essentially two paradigms by which one can generate flat electronic bands with non-trivial topology to allow you to probe the interplay of unconventional superconductivity, strong correlations, and non-trivial topology in a single materials platform. So on the left is a paradigm of creating flat bands from crystalline multilayers. And the canonical system is the rhombohedral metastable stacking of multilayer graphene. When you make this staircase configuration, and especially as you add more layers, you basically push all of the electronic states to the outer undimerized atoms on the top and bottom surfaces in a kind of SSH analog of polyacetylene. Because these low energy states are coming from the K and K prime corners of the Brillouin zone, they also carry a large Berry curvature. So the combination of the band flatness and the large Berry curvature allows you to have an interplay of strong correlations and non-trivial topology. On the other hand, there's also the paradigm of creating flat bands by engineering new superlattices with much longer length scales than the atomic lattice itself. So again, this was really pioneered by Pablo's effort about 7 years ago to study magic angle twisted bilayer graphene. But by now we know that there's many different combinations of twisting multilayer graphenes or twisting similar or dissimilar transition metal dichalcogenides, out of which you can get flat bands that often have non-zero Chern numbers. So by way of a quick advertisement, I just want to quickly flash some of the work that we've been doing on rhombohedral graphene multilayers, showing gate tunability of these various phases. So this is a sample of 7 layers of rhombohedral stacked graphene with a moire potential imparted by aligning to the bottom boron nitride. And then what we measure is the longitudinal resistance as a function of top and bottom gate voltage. And as I told you, some combination of those gives you the charge density and displacement field. The key results are that we see 2 pockets of superconductors, what I've labeled SC1 and SC2, that we can use gate voltages to toggle on and off. In addition, if we apply a very large displacement field, then we can also push the system into a very well-developed integer quantum anomalous Hall phase, where the Hall resistance is quantized to plus or minus h/e² at 0 magnetic field, depending on field training. So we can now think about experiments where we can use electrostatic junctions to try to match the superconductor with the 0 field Chern insulator state to try to look for engineering defect non-abelians. Another surprise is if we apply an in-plane magnetic field, then we see that, in fact, this entire resistive stripe at 0 field that hosts these 2 little puddles of superconductivity turns into one long river of superconductivity that flows through the phase diagram. Okay, so the point is basically that, these flat band systems and crystalline systems give you many degrees of freedom in terms of gate voltages and temperature and magnetic fields in various directions, from which you can generate interesting, strongly correlated and topological phases of matter. The real focus of my talk will be going back to, the kind of original flat band system in, 0 field 2D materials, magic angle twisted bilayer graphene. Here I want to just briefly explain the origin of flat bands in this material. We know that each monolayer graphene in the twisted bilayer contributes a linear Dirac-like dispersion at the K and K prime corners of its Brouillard zone. And so if we twist 2 graphene sheets by a small angle, then the top and bottom layer each give you a contribution of a Dirac cone, which sit close by a small angle of twist. Now, this isn't the entire story because we've not yet considered the interlayer tunneling or hybridization between the sheets. The consequence of turning that on is to basically open a gap at the crossing points at the gamma point of the Morey and Brouillard zone. And that gap, its size is basically set by the equilibrium spacing and the tunnel hybridization between the layers. So that's, in essence, a fixed quantity of the system, unless you squeeze the layers together. So what you can control is the twist angle. And you can find this so-called magic angle at which the offset of the Dirac cones in momentum space and the size of this hybridization gap conspire to push all of the low energy states down to a very small energy close to 0. We can quantify the width of this band by measuring the bandwidth W and calculating it as a function of the twist angle. And you find that it has this tendency to go towards 0 at the magic angle of 1.1 degree twist. At this angle, the relevant energy scale that's dominating the physics at low temperature is the mutual Coulomb repulsions between electrons living in this triangular Morey unit cell. And what we can find is that by quenching the kinetic energy, by flattening the band, we can invert the usual hierarchy that we typically see in graphene and basically put ourselves in a regime where low energy states are dominated by strong correlations rather than by the large intrinsic Fermi velocity of monolayer graphene. And this is just a summary of the many, many phases that people have seen in this system after, half a decade of intensive study, measuring as a function of the band filling factor on the horizontal, where 0 means charge neutral, 4 and -4 mean you're completely filling the flat bands with 2 spin and 2 valley copies. And then as a function of temperature and magnetic field. So the kind of high-level things that are seen across many different devices of twist angles near the magic angle is this kind of broad regime that forms around 100 Kelvin, where you start to get oscillations in resistance and seesaws in compressibility that have now been understood in some form as coming from a topological heavy fermion description of the system. At low temperatures on the order of a few Kelvin, you can start to break the spin and valley degeneracies of the system and get Mott-like insulators at integer fillings. If you go to 2 electrons or 2 holes per Morey unit cell and add a bit of extra charge, then you get domes of unconventional superconductivity. And then if you apply a magnetic field, you can change the topology of the correlated insulators and generate a cascade of Chern insulators with Chern numbers 4, 3, 2, 1, depending on their apparent band filling factor. Now, that was the kind of product of many, many groups and many years of work of making different devices and measuring them. And the reason that you have to do this is that, nature has been very kind in allowing us to access this physics at all, but forces us to deal with some challenges of these materials in real life. And one of the key challenges is that graphene is not actually a perfectly rigid lattice. So if we think about taking 2 sheets and stacking them, in our cartoon model, they're perfectly uniform, but in reality, these films are deformable. And it's just a fact of nature that these deformations are almost unavoidable when we make samples. And it's well known now that they kind of hamper the reproducibility. So it's very good for publishing more papers because every device gives you something new. But if you really want to learn what's going on in a single device, you can't be sure that you're not facing some pathological structural disorder that's giving you an unusual answer. And so indeed, there's kind of two forms of these inhomogeneities that go beyond just the standard charge fluctuations that we typically think about in lightly doped semiconductors. So one is that, if you have one graphene layer that you strain a little bit with respect to the other, the Moiré potential or the Moiré pattern acts like a magnifying glass for this strain. And you can see very substantial deformations, even at the few percent or a few tenths of a percent level, or even hundreds of a percent level strain in the individual lattices. And then a related problem is that you often form mosaics of slightly different twist angle as the system tries to contort into its low energy structural state. This strain issue is kind of prevalent across all length scales in the device. So there's scanning squid work from Elie Zeldov's group that shows that twist angles can vary on the scale of microns by fractions of a degree. TEM work that shows over the scale of a micron, you can see these Moiré patterns go from, say, big to small in the bottom right to the top left corner. And even on the near atomic scale, you can see that just translating by a few Moiré unit cells often gives you a very different area, depending on how high quality and how uniform the sample is. And the effective strain is actually quite profound when the band becomes very narrow, because any small changes to the structure are effectively pushing you away from the magic angle. So in the kind of pristine magic angle sample, then the Bishop-McDonald continuum model predicts that the flat band looks like this. But if we introduce some, tenth of a percent level heterostrain, so we just stretch one layer a little bit with respect to the other, we see that the bands deform quite substantially. So depending on which cut you look at through the Brillouin zone, you can see that these bands become, almost like flat and separated by some energy gap. There's an inherent topology that protects the Dirac crossings that's related to the C2 symmetry of the lattice, rotating by 180 degrees. Strain doesn't break that symmetry, so you need to maintain the Dirac points, but they often depin from the K and K prime corners and move towards the center of the Moiré-Brillouin zone. But in any case, what you can see is basically that, in this cartoon lattice, I've just stretched one layer that really strongly deforms the geometry of the hexagonal Moiré pattern. So what we want to think about is whether we can actually try to use strain as a resource, control it directly, and live with the, try to make the highest quality sample that we can make, live with whatever strain is baked into it, but then try to use strain as a control tuning knob to study how the physics of the system evolves, as we deform these lattices in plane. To do this, we borrowed a gadget that's by now pretty well known in the bulk crystal community. It's a piezo-based strain cell. So the idea is that you have three piezos that are arranged in in this line, and then you epoxy them to titanium sample plates. You apply the same bias to all of the piezos, but you pull the outer two oppositely from the inner one. So say if the outer two expand and the inner one contracts, that will open a gap in the sample stage. Or if you reverse the bias, then you can close a gap in the sample stage. This is work that we've been developing in my group and in collaboration with Professor Junhao Chu's group at the University of Washington, who's really an expert in these strain measurements, led by my PhD student, Jutao Ma, and by a former postdoc in Junhao's group, Jiayu Liu, who may look familiar because he's sitting right there. He's now a postdoc here at Rice. If you're interested in the technical details, these are some photos of all of the horrible stuff that you have to do to actually wire up the sample onto a Dilfridge insert. But if you have careful hands like Jutao and Jiayu do, then you can do this. And once you mount the strain cell onto your sample insert, you're basically able to just make standard transport experiments. Now with a new tuning knob, which is the voltage you apply to these piezos, which continuously stretches or compresses the gap in the sample plate and allows you to apply continuous uniaxial strain to the material. If you're interested in the details, the way that we do this is basically to laser cut holes out of a very thin silicon wafer, and then deposit our stack of 2D materials onto this narrow bridge and do all of the kind of standard device fabrication from there. Then we mount this sample onto the gap in the titanium sample plate, and then break off the two arms on the outer arms of the sample. And that leaves a very thin strip of silicon where the sample lives. And that's what we're going to try to stretch and compress. You can do a finite element analysis and convince yourself that, indeed this narrower bridge is really where there's a strong concentration of uniaxial strain. So we're basically shaping this wafer so that we're able to apply more strain to the material. And then hope basically that whatever strain we apply to the silicon wafer is actually transduced into the 2D layers that we care about. We can characterize the induced strain in the 2D material either optically by using well-known Raman benchmarks of graphene or silicon as a function of the piezo bias to figure out how much strain we get for a certain piezo voltage. And then once we know that, we can make electrical measurements of these gold meander wires that we evaporate next to the sample. When we stretch the material, the meander wire stretches a little bit and deforms by its Poisson ratio, and that changes the resistance that we measure. And so that gives us an on-chip electrical gauge. It's not perfect, but pretty good for how much strain we're getting. Okay, so the key result is to compare a control sample of Bernal stacked bilayer graphene with twisted bilayer graphene at the magic angle. Now, in the conditions that we're measuring this whole doped Bernal bilayer graphene on the top, we don't expect to be in a regime dominated by any symmetry breaking. And so we should just be basically measuring the strain response of kind of a standard metal. And within our resolution of measuring resistance, as we change the strain by just over 0.1%, we see basically no appreciable change in the resistance. However, if we do the same experiment for magic angle twisted bilayer graphene, now we can see that as we apply strain, here even less than 0.1% of strain, we can get changes in the resistance on the scale of hundreds of ohms. So evidently there's a big response in magic angle graphene that you don't see if you set the angle to 0. So we can quantify this with a figure of merit called the gauge factor, which is measuring the change in resistance normalized by the starting resistance divided by the total strain that we're applying. We can write this in a more convenient form, breaking it out into a geometric component, which is 1 plus 2 times the Poisson ratio. So for standard metals, the Poisson ratio is some fraction of 1. And so this geometric component should give you a value of order unity. If you see anything beyond that, then it's almost entirely coming from an electronic response, which is a change in resistivity as we strain the material. So we can calculate this gauge factor by measuring R versus doping at different piezo biases, calibrating how much strain we've applied, and then dividing the change in resistance by the change in strain. And that allows us to plot the gauge factor. So for this magic angle sample of 1.1 degrees, we see the gauge factor is very large, of order 100. We can look at samples slightly away from the magic angle, and the gauge factor, as long as we're close to the magic angle, is very large. 2 orders of magnitude bigger than what you would expect for a standard metal. So it's a strong indication that there's something electronic going on as we strain the material. I'm going to focus for the rest of the talk on this particular near magic angle device, 1.2 degrees, and try to analyze in detail what we see as a function of different tuning knobs that we have. So one thing that we can do is set the strain to 0 and measure the resistance as a function of the band filling and as a function of temperature. And if you're familiar with magic angle devices, you'll see these kind of familiar kind of step-like features near the integer filling factors as we raise the temperature. Then what we can do is sit at each band filling and measure the resistance as a function of strain, and then fit that to extract the gauge factor. And then do that for all temperatures and all dopings to construct this composite map of the gauge factor as a function of temperature and band filling factor. Now, there's an enormous amount of information encoded in this diagram, and it's mostly what I'm going to focus on trying to analyze for the rest of my time. The first analysis is to just take cuts of the gauge factor as a function of band filling at different temperatures. And what you can see are kind of 3 key observations. One is, as I've mentioned, the gauge factor is giant. It's orders of magnitude larger than what you would expect for a standard metal. Another is that it's evidently modulated by doping. Even at high temperature at 40 Kelvin, you can see these kind of staircase or step-like features near integer fillings. And there's also a very large temperature dependence. Now, it's interesting to think about the system in the context of measurements that have been made of the electronic entropy from measuring compressibility. So the top is work from Elie Zeldau's group, or Shahal Alani's group, and the bottom is from Eva Andre's group. And there's others that I haven't shown there, but they all broadly agree that at high temperature, you get this kind of dome of large electronic entropy, order kb per unit cell. And then as you lower the temperature, you generally get a dip around the charge neutrality point. So it's interesting that in some sense, the measured gauge factor as a function of band filling factor has a strong resemblance to these measurements of electronic entropy. At high temperature, you see this kind of dome-like structure, and then at low temperature, it develops a dip towards charge neutrality with maybe something different happening right at neutrality. We can fix the band filling factor near the charge neutral point and measure the temperature dependence of the gauge factor. And what you see is that it has this kind of weak diverging behavior until it reaches some threshold temperature, at which point it reaches a maximum and then goes back down. Now, something like this has actually been seen before in a cesium iron-based superconductor. So this particular stoichiometry is found not to have pneumatic ordering. So that you can see by measurements of the elastoresistance coefficients in the anisotropic B1G and B2G channels. Those are the red and purple, and they're basically zero. But what you see is if you measure the elastoresistance coefficient for the isotropic channel, where you're stretching in both directions, then that's the blue one, and that has this kind of weak divergence and then reaches a maximum and goes back down. And this was interpreted in the context of strain coupling to the electronic entropy of the system. And the maximum point is an indication of the coherent to incoherent crossover in the system, where you go from like a blurry, diffuse spectral weight at high temperature to some sharply defined Fermi surface at low temperature. So we can ask, is there a reason why you would expect to have some similar heavy fermion type physics in twisted graphene? And indeed, there have been many theories over the past few years in this direction. So there's work from Bernabik's group at Princeton that frames this in the kind of topological heavy fermion language, where most of the flat band is coming from electrons that are localized on the AA stacking sites of the Moiré unit cell. And those are kind of trapped in place, and their isospin moments are free to fluctuate independently, which leads to kind of a kV per unit cell entropy. And those hybridize with more dispersive parts of the band around the gamma point, which are made up of states from the AB and BA stacked components of the Moiré potential. And those are itinerant, and they can hybridize and scatter off of these fluctuating local moments. There's also related work framing these systems in related but other ways from Harvard and from Johns Hopkins, and there's many theories about this, and I won't cover them all. But they all broadly agree that, especially at high temperature, you expect to get these domes of kV per unit cell electronic entropy from something that you can consider as an analogy to a heavy fermion model. So we can analyze this in a bit more detail, basically by tracking this rollover temperature as a function of doping around neutrality. And we see that's these black points on the color map. It forms this dome-like structure. Okay, so one possible interpretation is that at high temperature, we're in this incoherent phase where we're dominated by these fluctuating local moments. At low temperature, some part of the Fermi surface forms sharply defined quasi-particles, and we're able to measure more conventional metallic behavior. And there's some evidence from DMFT calculations that near neutrality, you do expect to have these spectrally broadened Fermi surfaces that would be a necessary ingredient of this story. The last thing I'll focus on is what happens at 2 holes per Moiré unit cell. So in this case, what we find if we just measure resistance versus temperature is that it's approximately, although not exactly linear over a relatively wide range of temperature. There's been much work on this, trying to think about it in the context of the linear T behavior seen in cuprates and other strange metals. But I think there's not yet a consensus on how to fully understand this. The ultimate low temperature phase of this system at near 2 holes per Moiré unit cell turns out to be a valley polarized phase, and that has an anomalous Hall effect. And we can see that as we change the strain, we're able to tune the amplitude of this anomalous Hall effect. So we're able to control the nature of the symmetry broken ground state. But what I really want to focus on is the state above the temperature at which you order. So where the system is still fully isospin symmetric. What we can do is basically look at resistance versus temperature for different strains, and then use this to calculate the temperature dependence of the gauge factor. And again, we see this now kind of 1/T like divergence. But here there's a rollover that sometimes doesn't happen if we pick the right band filling factor. And if it does, it happens at a very low temperature, just a few Kelvin. We can compare this to the onset of the anomalous Hall effect, which is a detector of when we're getting symmetry breaking. And what we find is that the rollover, where we kind of cut off this divergence of the gauge factor, typically happens around the same temperature at which we form this valley polarized ordered state. So this 1/T divergence is a property of the symmetric state before any symmetry breaking onsets. We can analyze this within the context of the Curie-Weiss law. So in some sense, strain should be the conjugate field of pneumatic ordering. And you can replot these gauge factors as 1 over the gauge factor minus some high temperature asymptote versus temperature. And what you see is that they're very nicely linear over a decade change in temperature, with a corresponding Weiss temperature very close to 0. There's also, an analog story from iron-based superconductors, this time in barium-doped iron-based superconductor near a pneumatic quantum critical point. You can also see this very nice Curie-Weiss-like temperature dependence of the elastoresistance with a vanishing Weiss temperature. So that motivates the possibility that there's also some sort of pneumatic ordering around 2 holes per more unit cell, and that we're sensitive to this with strain. It's not a direct proof, but it kind of points in that direction. There's been a substantial amount of theory work, I think, starting with this paper and maybe from others before, predicting pneumatic order in the material. And there's also work measuring transport anisotropies around 2 holes per more unit cell from Pavlov's group that seem to suggest some sort of rotational symmetry breaking. And in the twisted tri-layer version of this material from Leo Lee's group, showing that these transport anisotropies can also persist to tens of Kelvin. So it's at least plausible that there's some sort of rotational symmetry breaking, even at very high temperature in the system. So looking forward, we'd really like to be able to deconvolve the isotropic contributions to elastoresistance from anisotropic contributions. One way to do this is to adopt this so-called sunflower type sample geometry, where we make the sample a disk and have many contacts around the perimeter. That allows you to measure transport in all different directions and basically decompose the full resistivity tensor, measure rho XX, rho YY, and rho YX. And that allows you to infer the full strain tensor. And that in principle could help us to separate possible contributions to this large elastoresistance coming from isotropic entropy-based channels and from anisotropic pneumatic-based channels. More generally, I think strain is now, using this technique, a resource that we can use to try to apply to many different strongly correlated, flat band or crystalline or Moiré flat band materials to try to study how it couples to unconventional superconductors, strongly correlated states and topological states across a variety of settings. All right, so with that, let me just wrap up and thank my entire group, but especially, again, PhD student Zhutao Ma, who's on the top right here, Dr. Xiaoyu Liu, who's here, and Junhao Chu and Zhao Dong, and many other collaborators I have at UW and around the world. So thanks, everyone.
Any questions?
I think you didn't mention superconductivity. How is this affected by the strain?
Good. Okay. So in the sample that we've been most successful at applying strain to, which was this one, we have a very, very unusual anomalous Hall ground state at 2 holes per Moiré unit cell. I don't know why, but it's a valley polarized state in all likelihood. And valley polarization has a pair breaking effect on superconductivity. I don't have the data here, but if you just dope the system and cool it to millikelvin temperature, it remains metallic. So in this sample, we didn't have the opportunity to study superconductivity. We've had other samples that were superconducting and on the strain cell, but we couldn't transduce enough strain. So basically, the long story short is we just haven't done the experiment well enough yet. And, I expect it'll do something and I just don't know what.
Other questions?
Thanks for the nice talk. I had a question regarding how does the quantitative value compare to many of the semiconductors resistance? Because like it can be pretty large, and also symmetry wise, is it related to the maybe the piezoelectric effect in this material?
Okay, so I know how to answer your first question. I think silicon famously has a very large gauge factor. I think that's also of order 100. And then some of these iron-based superconductors have gauge factors of order 100. So I would say it's comparable to or larger than other materials that have been measured before. And the way in which we extract the gauge factor is actually a lower bound, if anything, because we don't know quantitatively the precise amount of strain in the graphene. Whether it's related to some piezoelectric effect, this I don't know, and I'll have to think about more carefully.
Yeah, so in the iron-based superconductors, there was some discussion about if you decompose into different symmetry channels, the isotropic channel would actually not just be reflecting pneumatic correlations, could it be effective mass is changing versus temperature, etc.
Yes.
So how much of that can be filtered out in the analysis?
So I think that this is the most careful way that this has been done, to my knowledge, where you basically try to decompose the different anisotropic and isotropic elastoresistance coefficients, and then compare whether the effect that you're seeing in the gauge factor is predominantly from the isotropic channel or predominantly from the anisotropic channel. And the story in iron-based superconductors is that the stoichiometry determines what the answer is. Mm-hmm. Right, in the cesium one, it's almost entirely from the isotropic channel. In like barium doped pnictides, then it's almost entirely from the anisotropic channel. So I think when it's from the isotropic channel, then the considerations you mentioned about strain coupling to effective mass are the right direction to go in.
But in the current data that you have, is there some sense that the isotropic part has been filtered out, or is it still in there?
They're both still in there. So the way we make the measurement is basically to measure resistance along the axis of uniaxial strain. So we basically have no idea how to do the symmetry decomposition. And I would really like to, of course, and to do that, we need to make these more complicated, sunflower type sample geometries.
Beautiful data.
Thanks.
All right, let's thank Matt again.